Hello, good afternoon. I'm really very happy to be with you today. We will start our lecture. I'm sorry for the short notice. We had to cover this topic. It's involved in our midterm, so we had to finish it today, inshallah. I thought to record this lecture in order to put you on the right track with limits. And also, I've decided to call it into limits as we will talk about limits and about the various types of limits, either in for functions in single valued functions or functions in several variables or in vectorial functions or vector valued functions, as you will see. The most important thing that I want you to keep in mind is please try to solve as much as possible and try to do as much as possible from training by solving exams, by solving exercises using your pen. This is really very important. As our study plan goes, we will cover today in this session the limits by definition. Let me grab my pointer just in a second. Just a second. Okay, here's my laser pointer. So we will start by the definition of the limits and the content. I will go through the squeezing theorem just very quickly. Then we will continue to limits along paths through our lecture today. As I told you, nothing to worry about. All I want from you is just go through it. I've already sent the PDF for you, so you have it at the time being. Please try to resolve these problems more than once. And as I told you, use your pen. This is really important. This is really very important. Once more, in this session, inshallah, this is session number 7 and number 8. I will go through limits of function, definition of limits, examples in R and R2, the squeezing theorem, and the limits along bosses altogether. I've mentioned this plenty of times, but I'm repeating this for you. It's really very important. Okay, it's really very important. You have all the resources on Moodle, and please try to go through Moodle more than once. In this slide, I'm putting you my picture duplicated just to stress on the fact you need to go to Moodle, watch the vids, watch the slides, and also all of this beside all the slides that you have. Also, as you know, and as usually I say to you and mention, you will have the recorded lectures all on my YouTube channel. Okay, I will start by a limit at a point. If we look carefully, this to this scheme or to this uh, 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 photo, you will find the following. If I'm trying to see the limit of f of x when x tends to x node at this point, I hope my laser pointer is working right. You will see near point x node, and as x changes and reaching x node from the left or from the right, the function by itself it reaches step by step the value of y node, and as you can see. And y node is in the range of the function f of x. In this case, the limit exists. If we study the case of the limit of this function f of x at x1, and also coming from the right and from the left, you will find that this function is defined by more than one function. From the right and from the left, both of them are tending the same value of f of x, which is y1. So the limit also exists and it's equal to y1. Even if y1 is not in the domain, I'm sorry, if x1 is not in the domain of f of x, and although y1 is not in the range of f of x, but it will tend to it. And that's the real meaning of limits. If you look closer to x2, and you can see from the left and from the right, if I'm trying to approach x2 from the right or from the left, you will find that the function tends to negative infinity. And of course, negative infinity is not a part of, or it's not a defined value, but since the function is coming from both sides into negative infinity, so the function tends to negative infinity from both sides. All of this is completely different once you start studying the limit of the function at x tends to 0. When x tends to 0 from the right and from the left. If it comes from the left, you will find that the function is going to change, reach y 0. And if it comes from the right, you will find that the function is tending to 0. And these two functions on the y, two values on the y are not equal to each other. This is the meaning, or that's the case when the function is not, the limit of the function doesn't exist. So from this, as you can see from this scheme or from this graph of this function, this sketch of this function, you will find that it show you the cases of the function if it tends to x node and it exists, and also both x node and y node are points from your domain and range, and also it show you when the function is tending to a point, accumulation point, and it is not in your domain or range, or when the function f of x tends to certain value and the corresponding is negative infinity, but it is still inside your domain as you saw. But the limit existence equal to negative infinity, and also the worst case of having f of x not defined, or the limit doesn't exist. The coming slide, you have plenty of examples. Always the first step in solving or issuing a limit is to try to substitute. So if we look closely, the first problem, which is studying the case, if x tends to 0, what's going to be the case or the value of f of x expected? If I'm going to substitute for x equal to 0, and that's the first step we usually do by limits, you will find 0 to the power of 2 minus 2 times 0, which is 0, minus 4. So the denominator is equal to negative 4 and divided by negative 1. So the result is positive 4. And that's for the first problem. If you go for the second one, the second problem contains x to the power of 4 minus 4 times y to the power of 4 divided by, as you can see. And this is a function in several variables in both x and y. Also, if I try to substitute by x equal to 0, y is equal to 0, you will find that the value of this function is undefined. It's 0 over 0. In such a case, it will be really very helpful if you use simplification, if it is possible, to eliminate this this undetermined value. So I can, as you can see from the nominator, it's a perfect square. So I can factorize it to be x squared minus 2 times y squared times the second bracket. It's going to be x to the power of 2 minus plus 2 times y to the power of 2 divided by this value, take 2 as a common, and then you will be able to eliminate the x squared plus y squared from the denominator with the same bracket from above. And so you will be able to solve this limit. I believe it's going to come to 0. If you look to this problem and they make a substitution, it's going to be 0 times e to the power of 0, which means it's going to equal to 0. For this problem too, it's direct substitution. It's going to be 1 plus 4, so it tends to 5. There is no problem in that. The example in 3.3, this will need an extra work from you. I think when we get a chance, inshallah, I will solve it to you in our tutorials next week, inshallah. And this is the idea till we come together. I will try to expand e to the power of x plus y using Taylor expansion or so, and then subtracting negative 1. Then I will be able to diminish and simplify this value of x, and so I will be able to get to meet my expectation of having this limit exist. The problem will be like this. If they exist, the following the direct limits and the limits by the definitions, as we did go through the previous problems, as you can see. The first one, when you and the first step, just to try to simplify or try to substitute at the first. If the function exists, it's okay. If not, I will try to do some simplification. So these three problems, really very simple, go through either in real single valued functions or functions in several variables, as you will see. So for the first one, if I replaced each x by 2, you will find the value is -3, and it is a determinant value for your limit, so it needs no extra work. Exactly the same for the second one, just replacing x and y by the values that's they are tending to, which is 1, and so you will get your value. For the third problem, once you start to substitute by 0, you will end up having 0 divided by 0, which is undetermined quantity. If I try to just factorize the numerator, it's going to be x minus y times x plus y. Now I can cancel these two terms, which means I will eliminate the 0 factor from the denominator. Once you eliminate the 0 factor from your denominator, you will be able to find your limit directly. And this is what happened. I canceled x plus y from the both denominator and the denominator. I ended up having a limit of x and y tends to 0 for x minus y. Just making this right substitution, the value will equal to 0. It's really crystal clear, as you can see. In general, this is, as we saw in the previous sketch for the function, this is mainly what usually happen in limits. This is extending from left and right, from the red arrow and from the blue arrow. And on the y-axis, this is actually what's happening for the function f of x. It is approaching certain value in y. And in this case, the limit for this function, when it x tends to a, the function will tend to b. This can be defined in general in this form. So I can say let f be such that, or the domain where the domain belongs is a subs is completely contained in Rm and into Rm, which is the range of this function. And if A belongs to Rn, so A belongs to the domain, and the B will belong to the range of this function. Once more, let f such that D is a subset from Rn into Rn, and the A belongs to Rn, which is an accumulation point of a domain. B belongs to Rm, it is the limit of f at point A, and represented by limit f of x when x tends to A. It is the value of f of x once x tends to A. And this will happen if and only if. This is very important. This slide is very important for you. And this is when this happens. So that's the complete definition of the limits using definition. It is beautifully written. It is stating that if you have a function and your independent variable is approaching A, the function by itself will approach B if and only if for every delta greater than 0, there exists epsilon greater than 0 such that the open ball x with center A with radius epsilon will lead to the image of your function, the open ball at the image of the function centered at B will have radius equal to delta. Once more, I've wrote it for you in English. So for every delta greater than 0, it is possible, or there exists, an epsilon which is greater than 0, such that the x is an open ball with center at A with radius epsilon. Its image is an open ball with center B and radius delta. This is how to find or to be sure that the limit of a function already exists. So actually, I will use the limit of f at a point A in order to check the value of the function or the value of a limit at a certain point when x is tending to a certain value. This is really major. And I will depend on this comment on all our coming problems. So I need you to memorize it. So once more, let f such that it is within the domain from Rn into Rn, and the A belongs to Rn, so A is in the domain, it is the independent variable, an accumulation point of D, where B belongs to Rm, it is the limit of f at the point A, and it is denoted by limit x tends to A for an f of x. It will exist if and only f. For every delta greater than 0, there exists an epsilon greater than 0 such that the open ball x with center A is hasn't had a radius epsilon, which will lead to, or it's a sufficient condition to have the image open ball at centered at B uh, and radius of delta, as you can see. We will train on plenty of problems, as you will see. But before we do so, I want you to keep in mind these quantities. You will need them. It is like the Schwartz inequality. It's like the triangular inequality that we went through previously. And it is really very important. Once I saw this symbol, it is the norm of xy, and it's equal to the square root of the sum of the squares of the two components that exist. Also remark the norm to the power of 2, and those expressions will be used, as you will see, extensively in the coming limits or in the coming problems, as you will see. So the norm to the power of 2, it's simply x squared plus y squared. Also, I want you to remember that the absolute value of x is less than or equal the norm of x plus y. That means the absolute value of x is less than or equal the square root of x squared plus y squared. Also, x squared by itself, it is less than or equal the square of the norm, which is x squared plus y squared. Okay. Also, the absolute value of y is less than or equal the norm of x plus y, and y squared is less than or equal the norm of x squared plus y squared, which you are adding. Y squared for sure, it will be less than the value of x squared plus y squared. The worst case scenario will happen when x is equal to 0, so they will equal to each other, as you can see. Also, I have the absolute of the plus or minus of a plus b. It's going to be less than or equal the absolute of a plus the absolute of b. If I have an absolute to the power of x, it's going to be less than or equal the norm of xy to the power of k, where k is greater than 0. These quantities play a major role in how to prove the definition and the relation between epsilon and the delta that you will see through the coming slides, inshallah. I will start with some problems within, as you can see, from a single valued function from R to R. Let's start by this direct limit, which is x squared minus 4 over x minus 2 equal to 4. I can, of course, solve this problem directly. If you try to substitute by 2, the limit's not going to be defined, but it is a removable case. I can factorize x squared minus 4 to be x minus 2 times x plus 2. X minus 2 will cancel x minus 2. I will end up having x plus 2. So just to make a substitution, you will have the value of your limit. But instead, I will use the definition. The definition states that I can find delta greater than 0 such that, and for it, there exists epsilon greater than 0 such that the open ball at x, the open ball for x at center 2 has a radius of epsilon and will lead to the image of the open ball of f of x at center at 4 is less than delta, as you can see. stating this with the magnitude or with the absolute, or with the absolute relations, in the case of functions from R to R, it will make no difference. Before we start, I want you to keep in mind, I usually do it like this way. If you move to near to x, so it's going to be x minus 2 less than epsilon. And I know directly that epsilon is less than or equal to delta. And I want to see f of x minus 4 less than or equal to delta, as we will see. I will start from this guy. So step number one, I will get f of x minus 4. I'm checking if this limit is equal to 4. This is actually what we are doing. So in this part, let me just wait for a second. In this part, I'm not finding the limit. No. I'm just checking if the proposed limit is actually the limit of f of x or not. So already those problems are already solved. So I know that the limit of x tends to x squared minus 4 over x minus 2 is equal to 4. I'm just checking using the definition that it is 4. It may seem to you it doesn't make any sense at the time being, but it will do down the road, as you will see. Now, f of x minus 4, so all I have to do is to just replace f of x by its value, which is x squared minus 4 divided by x minus 2 minus 4. And I'm getting the absolute of this one. So all I have to do is to get a common denominator for both of them and factorizing the denominator. So I would have x plus 2, x minus 2 divided by x minus 2. I can actually eliminate the two brackets together, x minus 2 is x minus 2, and I will end up having x plus 2 minus 4, which is x minus 2. That's the main the value. So I've started with the function minus the limit. I ended up with the definition of the open ball at x center at 2, which makes sense. It's less than epsilon, as you will see. So x minus 2, I know it's less than epsilon. So we have now for sure that's f of x minus 4 is less than epsilon because they have the same value. And since x minus 2 is less than the epsilon, or the open ball at x whose center A has radius epsilon, so f of x minus 4 is less than. And since epsilon is less than delta, okay, then f of x minus 4 is less than delta also. I've succeeded in holding or having hold on the definition. That's a one relation between epsilon and the delta. That's epsilon is less than or equal to delta. So for every delta greater than 0, there is an epsilon which is greater than 0, less than or equal to delta, where I will have x minus 2 less than epsilon, which leads to f of x minus 4 less than delta, so the limit is equal to 4. Perfectly done. I will repeat all the steps once more with another problem. I want you to memorize these steps. It's a constant steps, but the experience will come with more problems. Here I'm checking limit x squared at 1 is equal to 1. I want to check this value using the definition. So once more, searching for delta greater than 0, where there exists epsilon greater than 0 such that x minus 1, so move this one beside x minus 1 absolute should be less than epsilon, and leads to that the open ball of the function at the value of the limit has a radius of delta, as you will say. Okay, done. I will start once more from the definition of f of x minus 1. So I would start with f of x minus 1, which is going to come up to x squared minus 1, as you can see. All I did is replacing f of x by x squared. Now I have x squared minus 1. As you can see from this relation, I can, instead I having a perfect square, the difference between two squares, so I can factorize it to be x plus 1, x minus 1. Which means that this value will equal to the absolute of x plus 1 times x minus 1, as you will see. So it's an x minus 1 less than epsilon. So f of x minus 1 is less than epsilon times x plus 1, as you can see from the definition of x minus 1 to epsilon. So all I did is just making the substitution. Since epsilon is less than 1, so now I can make the change that x is actually in between because I have an absolute epsilon plus 1 and the greater than 1 minus epsilon. And from this point, now I will consider, as we already considering that epsilon is less than 1, then x is less than 2, as you will see. Now, for epsilon less than or equal to 1, I have, if you make the substitution by x equal to 2, 3 theta is less than or equal to delta. So the perfect value, the relation between epsilon and the delta is epsilon is less than delta over 3 as you saw. So from this relation, I can now sure have the definition in front of us that for delta is greater than 0, there is epsilon greater than 0 and less than the minimum of delta over 3 and 1. So x minus 1, the open ball at x with center 1 is less than 3, which will lead to the value of the function minus the limit as an open ball will be also less than delta, and which leads to that the limit exists and it's equal to 1. Similar trend, exactly the same. And similar argument, discussion will be running if you have a function in several variables. Like this problem in front of us. I have xy tends to the origin and the value of the function expected to be equal to 0. So once more, we will use the definition. That's for every delta is greater than 0. I need to check if there is epsilon greater than 0 such that the norm, here I can't replace the absolute, okay? That's the norm of x minus y, of xy minus the origin. So it's like moving 0 beside the x and y. It's less than epsilon, which will lead to the image of the function minus the limit should be less than delta. Once more, for every delta greater than 0, it is possible to find an epsilon which is greater than 0, such that the xy is an open ball with center at origin with radius epsilon, and its image is an open ball with center 0 and radius equal to delta. This is what I'm going to discuss. What I have to do, exactly like previous step number 1, getting the f of xy minus the origin f of xy, which is x squared y divided by x squared plus y squared. The 0 here plays the rule of the origin. So it will be just only x squared y divided by x squared and y squared. Now I need you to memorize the relations that I stated for you before we start this part. From all of this, I can know that x squared will remain positive. And for sure, y, if I took y absolute, divided by the square of the norm, which is x squared plus y squared, this value is gonna for sure be less than or equal. Instead of dealing with the absolute of y, it is the square root of y squared. And replacing x squared by x squared plus y squared, for sure, that's why we changed the equality into the inequality sign. So we, instead of having x squared, added x squared plus y squared, and this will play a role with the denominator. So actually, it is the experience in solving such problems that helped you in expecting that I will replace x squared by x squared plus y squared, as you can see. Now I can cancel this guy with the denominator, because if you remember x squared plus y squared, it is the square of the norm of x and y, or the magnitude of x and y. So I will delete them together, which leads to it is equal to the root of x squared plus y squared. The root of x squared plus y squared, it is the magnitude of x and y. Now, from what we are in at the time being, you will discover the following: that I've started with f of xy minus the origin. I've ended up with having the norm of x and y, which is for sure less than epsilon. And so we will have f of x minus 0 less than epsilon. From the beginning, I have the assumption that's epsilon is less than delta. Their values is compensating very well. that we have at the time being f of x y minus 0, which is less than delta. So it makes sense it's less than, I'm sorry, less than epsilon. So it makes sense it's less than or equal to delta. So one relation between epsilon and the delta is given, that's theta is epsilon is less than or equal to delta. And so for every delta greater than 0, you will have epsilon less than delta, in where the open ball at xy with center at the origin has a radius of epsilon. I will find for the image an open ball at f of xy minus the value of the limit, and it's equal to delta. And now I'm sure about the check that the limit exists and it's equal to 0, as you can see. I didn't want to stop at this point. I've continued this part by more problems for you. This is another example because I know the taste of these problems using the definition. It needs plenty of practice. So this problem, for example, it's a real function of several variables. Also, the domain R into R. As you can see, it is the limit of xy tends to the origin, x squared y squared divided by x squared plus y squared equal to 0. So once more, I will use the definition that will work fine, very good with the norm, as you can see. So I will start proving this relation once more. For every delta greater than 0, it's possible to find an epsilon greater than 0 such that the xy is an open ball with center at the origin with radius epsilon, and its image is an open ball with center 0 and radius delta, as we can see. So I would start with the function minus the value of the limit, which is 0. Here is the function x squared y squared divided by x squared plus y squared minus the origin, so it will be the same. I know now from the relations, this is the magnitude or the norm to the power of 2. I have x squared y squared. There is no meaning for the absolute value. They will be the same. And for sure, those two values, x squared is less than x squared plus y squared, and y squared is for sure less than x squared plus y squared. This is why we changed the equality into the inequality sign. Now, replacing these values by magnitudes or by norms, this is going to be the norm of xy. This is going to be also the norm of xy. I can cancel two of them together, and I will have x y to the power of 2, which means, يا شباب, إن إحنا, which means, as you can see, that for xy is less than epsilon, we will have f of x minus 0 less than epsilon to the power of 2. Because I started that x y minus 0 is less than epsilon. Now I have x y is to the power of 2, so it's epsilon to the power of 2 equal to delta. So the relation connecting epsilon and the delta is simply epsilon is less than or equal the root of delta. And for the function f of xy minus 0, for sure it's less than epsilon, less than or equal to the root of delta. So the relation between epsilon and delta is given by epsilon is less than or equal to delta, and succeeded in finding delta greater than 0, where epsilon is less than the root of delta, and also the magnitude less than epsilon, blah, blah, blah. It's the same exactly like we did previously. Also, I want to be generous in this part and to show you also a vector valued function of several variables moving with the same trend. So in this situation, I will do exactly the same like what we did. Once more, for every delta greater than 0, it is possible to find an epsilon greater than 0 such that the x is an open ball with center the origin with radius epsilon. And its image is going to be an open ball with center the origin and radius delta. You can find that easily. So I will do exactly the same. Here I can't use the absolute relations, but I can use directly the relations related to the norm as you will see. So once more, I will start with the function step by step. Once you see this value, which is x squared over the first component, second component, is the norm. For the norm of f of xy, it is the square. root of the square values of the two components. That's the first component to the power of 2 plus the second component to the power of 2 under the square root. So I will start using the powers. So it's going to be x to the power of 4 times y square divided by the denominator, same with the second element. Remark, I will use advantages from the relations that I gave you previously. Now I will replace, please do focus in this. Please look at this. See the power, how it's working with the denominator? Now I have the denominator x squared plus absolute y to the power of 2, which is for sure is going to be, once you decrease the denominator, then this value is going to be less than that guy, because the denominator here is less than the denominator in this side. So this value is going to be greater than that value. See, denominators are the same, but I've reduced the denominator. Wow, that's a good move. That's a good move. Just playing in the denominator in order to get the inequality, as you can see. So x to the power of 4 y square is divided by x to the power of 4, and same for the second component, which is less than or equal to the root of y square plus x square, which is the norm, as you can see, of x and y, or the magnitude of an xy. Since now I've started with the function and ended up with the norm of x square y square, which is exactly like having the norm, which is known from the beginning, it's less than epsilon, so the function is less than epsilon. Similar debate, so epsilon is exactly like less than or equal to delta, and I can find the relation now between epsilon and delta, which is given by epsilon is less than or equal to delta, and the proof of the limit is already there. In a similar manner, if you look once more to this problem, a similar debate will be exactly the same. You will move with the same steps in order to comfort you, make you feel it is exactly the same sequence. There is no problem whatsoever. I will start with the function minus 0, which is the norm. That's the square of the square root of the squares of the two components, as you can see. See how the problems are really very near to each other. Once more, it can be decreased to be x to the power of 8y to the power of 8 divided by x squared y squared to the power of 2. Now I have to think just a little bit to change this equality into inequality. It's really very easy once you just manipulate the nominators by, instead of having x squared, I will increase it by x squared plus y squared to the power 4 and x squared plus y squared to the power of 4, which can be got as root 2 of x y to the power of 2, all of them to the power of 4. So the square root will go on 2, which is going to be root 2. The square root will act with 4. It's going to be to the power of 2. I can cancel two of them together. So this is the case that I will see. Now I have the relation that this function ended up with root 2, but it is the magnitude of xy to the power of 2, which means epsilon to the power of 2. So the relation now for the image is once xy is less than epsilon, the image will be less than root 2 epsilon to the power of 2. That means this value is less than delta. Now I have the relation connecting the epsilon and the delta, which means epsilon is less than or equal to the root of delta divided by the root of 2, as you can see. And so same relation, same statement. I now have proved that this is the relation regarding this part. A similar debate and on more examples, those are some examples on all types of functions on the evaluation of limits by definition. I will start by R and R. That's also an example, direct one. If you try to use this problem or to find the limit of this problem directly, it has no problem because it's an x squared minus 7x plus 10 equal to negative 2. It's a direct substitution by 3, so it's going to be 9 minus 21 plus 10, which is going to lead to negative 2. If I want to check this limit using the definition, yes, I can. Yes, I can. So how to do it? All I have to do is to get f of x minus b. So it's going to be f of x plus 2. I will replace f of x by x squared minus 7x plus 10 plus 2. See, I can how I'm going to manipulate this part. Actually, it's really very tempting to, okay, well, let me wait. I can, instead of dealing with negative 7 of x, I can make it negative 7x minus x. And in this case, I will be able to do completing square. Also, I can add negative 6x and positive 6x. So this is actually what I'm going to do. I will add negative 6x plus 9 and subtract 7 6x minus 9. If you see those part or this part, I've added in order to make my life easier in making completing square within the first part, and then the remaining parts will be added together, leaving me with negative x plus 3, as you will see. In this shape, I can take x minus 3 as a common. This is the case that you will see. They have x minus 3 to the power of 2 minus x minus 3 absolute, which is for sure less than or equal the square of the absolute of x minus 3 plus x minus 3 absolute. Now, if you remark, x minus 3 is less than epsilon. So this means if I used this substitution here, I can guarantee that this is epsilon square plus epsilon. I have also something to add for you. I know that epsilon is less than 1. So for sure, epsilon to the power of 2 is less than epsilon. And that's a new move. That's a new card I can use. So now I will use those replacements that epsilon to the power of 2 is less than epsilon, replacing epsilon to the power of 2 by epsilon. So the inequality works fine, that f of x plus 2 is less than 2 of an epsilon, which is for sure I can find that they are less than or equal to some radius of delta. And the relation connecting epsilon and delta is now easily to be done. That's the beginning of the problem. And that's the relation that I used between them. That's the end of the relation between epsilon and the delta, as you can see. So now epsilon will be the minimum of 1 plus delta over 2. So x minus 3 less than epsilon will lead to the f of x, or the image plus 2 is less than delta, and so the limit hold. Another problem with the same definition, but in this case, I will be dealing with function of several variables into R. So I'm dealing with the function of R2 into R. This is my function, that's the value at the origin, and this is x tending to the origin. So once more, for delta greater than 0, there exists epsilon greater than 0 such that xy minus the origin is less than epsilon and greater than 0. I will do exactly the same. So the objective is to find the relation connecting epsilon and the delta. The strategy will consist of beginning by finding the upper limit of f of xy minus b. So I would start with 2xy squared, x squared, y squared, exactly like what we did previously. Minus 0 is less than delta. And this is going to leave me with 2xy squared divided by x squared, y squared. Now you are professional in this. So I know that the denominator will be, because it's a power 2, so it's the norm to the power of 2. As I told you, as more problems you will solve, you will be able to expand them, as you can see. It's going to be 2 absolute of x y squared. And then now I can use the inequality. That's for sure y square is less than or equal the norm of x square y square. And for the absolute of x, just only it's going to be less than the norm of x plus y. Now I can reduce it to x and y. Now I have 2 theta less than or equal to delta. The relation between epsilon and the delta is clear. Epsilon less than or equal to delta over 2. So once more, I found that the norm of x, or the open ball of xy, was centered at 0. It has a radius epsilon. And so the image, same song, the image minus 0 is less than delta, and so all the the remaining steps, all the remaining steps stay the same. Now, for show using the definition for this problem is a little bit different. The previous ones were xy tends to the origin, but in this problem, the xy is not tending to the origin. In this case, I can do change of variables. See how I'm going to make the change of variable. I will consider moving one beside x, so it's going to be x minus 1. We will consider it x capital. The moving 2 beside y, so y minus 2, I will consider it y capital. Now the limit for x capital, y capital will be for the origin. And once more, I will regain the limit, that limit x capital, y capital into the origin will equal to, instead of dealing with x, I will be dealing with x capital plus 1 to the power of 2. And instead of dealing with y small, I will be dealing with y capital plus 2, as you can see. And if I make a substitution, it will equal to 3, exactly direct, same steps. I will start again getting the value of the function minus 0 and making the substitution, okay, and simplifying, same steps as before. And I will be able to find the limit, as you can see, taking advantage from all the previous relations. Now I will have the relation of 4 epsilon less than delta. So once more, I will be able to find that epsilon equal to delta over 4. I will take the minimum of both of them, and now I've proved the limit exactly like before. Also, I've added another problem in vectorial or functions in more than one variable, or vector valued functions. Similar debate exactly. And this problem will move directly. I will take the function minus 0 and 0. I will take advantage from that the norm of u and v, it is the square root of u square plus v square. So the first component to the power of 2, the second component to the power of 2. This is also, we did exactly the same problem previously. So now I will expand them. As you can see, the second step, I will have the absolute, the changing from the equality into the inequality. So I will change the x and y by the absolutes. And then, due to this replacement, I can eliminate x bar 8 with x bar 8 from this relation. And also, as again from replacing xy by the absolute values of absolute x and y, I will be able to have this function on this form, which means it is the norm of x and y for sure less than or equal to the norm, to the norms of x and y plus y square, which can be actually a perfect square, where I will get the benefits of canceling the square root with power 2, and I will have 2 times the magnitude of x and y. Now I have the relation. Absolute, the magnitude of xy is less than epsilon. So I have 2 epsilon less than delta, which leave me with epsilon less than delta over 2 in a similar manner. Now I have the value. The squeeze theorem, it's really very, I'm not going deeper into the squeeze theorem. I will go through it quickly just to make you understand that if I have F, G, and H, and it is running from Rn into R, if both F and H, Allah Akbar, if both F and H, both of them can tend to a certain value, so the function in between of them will be tending to that value also. So if you remark, I have F, G, and H within the domain of Rn that will be modeled or mapped into R. If A belongs to Rn and it is an accumulation point to the domains of function F, G, and H, that there exists alpha greater than 0, where h of x is less than or equal f of x is less than or equal g of x, where x belongs to all of them. So if the limits of h and g equal to b, f of x must equal to b. The coming slide is stressing on this fact. This is f of x, that's h of x. If h of x tends to b and f of x tends to b, and g of x is sandwiched between both of them, then g of x also will tend to be as you can see, or will tend to the same limit. Now we will come to the last part of our lecture, which is limit along a path. And this is really very important. I've tried to summarize it for you as much as possible. In all the previous slides and discussions, using the definition, we saw how to prove that a given value of a point or a vector is the limit of a function, the given value of the limit. So actually the limits was evaluated, you have the limit, and you are just checking if the limit matches the definition or not. But how to choose which value can be taken as a candidate for the limit, this is going to be the discussion of the coming slide. So limit of a function f from R into R. In the case of no intermediate indeterminate forms are arising, this is going to be really very simple. So if I am dealing from R into R from the domains, from the domain of R to R, like this problem, limit x tends to 0 for 2 to the power of x minus 3. Once you make the substitution, you will have no problem because you will have 2 to the power of 0, which is 1. In a similar debate, if we are in functions with several variables, like this guy, and if you make the substitution replacing both x and y in everywhere by 2 and 1, you will have also defined the value. So I have no problem with that. But in case of having functions with indeterminate forms and arising to you, in this case, my troubles will start. Let's see this problem if we can simplify, or if in the cases if we can simplify. So in this problem, we will have limit x tends to 0 for the root of 1 plus x minus 1 over x. And for this problem, if you make the substitution, you will end up having 0 over 0, which is indeterminate quantity. But if I do some simplification with this function, I believe I will be able to find the solution. So all I will have to do now is to multiply those guy by the conjugate of root 1 plus x positive y on both denominator and the denominator. Once you do this, you will be able to eliminate the square root from the denominator, and then you will be able to cancel negative 1 with positive 1, and canceling x with x, which will leave you with the limit of 1 divided by the root of 1 plus x plus 1. Putting x tends to 0, then the result will be 1 over 2. If I tried also to solve x minus y divided by x squared minus y squared, also same result if I'm using the substitution of 1 and 1. I will be ended up having 0 over 0. That's an undetermined quantity. But if you remark, we can factorize the denominator, which is a difference between two squares. Now I can cancel x minus y with x minus y, which will leave you with 1 over x plus y. Just replacing and make substitution, it will equal to 12. And once more, there is no problem whatsoever. In case of determining limits of a function, no, what if we couldn't find, I'm sorry, this is now, not no. Now, what if we couldn't find or couldn't simplify the function expression arises? In this case, we will need to use the definition of the limit studied previously, just to see if if there is a proposed value for the function to be a limit, and check if it is possible or not. This is why I'm going to use the definition. And if you remark, I have to come up with this value of b. I have to find the way in order to speculate the value of b in order to use the definition like the previous slides. I will start with one-sided limits on functions from R to R. A function of f defined a neighborhood of x node has a limit of x node if and only if it has left and right inequalities and equal to each other. And in this case, this function, it has a limit. One of the famous actually examples on this, if I want to take the limit of x tends to 0 of absolute x over x, If you remark, this limit doesn't exist. I will show you how it doesn't exist. If the absolute, if I'm talking about x to the positive, to the right, and I'm sorry, x tends to 0 from the right or 0 from the left, I will be dealing with these cases, 0 positive, 0 negative. In case of 0 positive, it's going to be x over x, which is going to be 1. In case of 0 negative, it's going to be negative x over x, which is going to be negative 1. I can use the definition of the limit, which is when x equals 0 plus h, or 0 plus h, and h is a very small tiny value that tends to 0, and h is greater than 0, they will be cancelled together. In the case of 0 negative, it will be with a negative h, and so once you try to eliminate them, you will have 1 and the negative 1, which they are not equal to each other, and in this case, the limit doesn't exist. Instead of doing this part, I can simply replace absolute x in the case of 0 positive to be x positive, and be negative x in the case of 0 negative. They will be cancelled and you will have the same result as you can see. Once more, if you look carefully this function sketch and discuss the cases at -4 and when x tends to -4 from left or from the right, both of them the toward 2. So the limit exists in this case and it's equal to 2, as you can see, the right hand and left hand. If I'm discussing the case of the limit at 1 from the left and from the right, you will find that the values of the limit is not going to be equal, so the limit doesn't exist. If I want to discuss the limit x tends to 0 from left or from the right, from the left, the value of the function tends to 5. From the right, the value of the function tends also to 5. So the limit exists and is equal to 5, although the function is not defined at x equal to 6 because it's equal to 2. It's not equal to 5. And this is the case when the value of the limit doesn't meet the value or doesn't equal to the value of the function definition at this point. Once more, limit of function from in several variables, and this is dramatically it changes other than the limits of functions in one variable. In the case of functions in several variables, I will suffer from the true reality of that. The function will approach this point from plenty of places, from hundred thousands of routes. So once more, when investigating whether a function has a limit at a point A, no restriction can be made on the way in which x approaches A, except that x must be in the domain of df. So I have plenty of curves or functions to study in order to get the limit of a function in several variables. What's going to make our life easier is to know about the following. This is the first method of them, which is the directional limit. A directional limit of a function f from Rn to Rm when the argument approaches x node is a limit of f when the argument approaches x node along a straight line. So if I want to discuss the relation of f of xy equal to xy over x squared y squared, I can use several methods or several lines. Like first, if I use y equal to x, now I will have the advantage of decreasing this function. Instead of being 2 in 2 to be 1 in 1, I will use the relation of y equal to x. Once you use y equal to x, I will replace the y's that exist in the limit by x's. So it's going to be 2x times x divided by x squared and x squared, and in such a case, the limit is going to equal to 1. This is one of the proposed ways. Another one can use y equal to negative of x or x equal to 0. If I used equal to 0 and use this line or this direction, the problem will be as the following. This is the case of x equal to 0 or y equal to 0. For this problem, it will make no difference. So if I'm discussing the case of x tends to 0, all I have to do is to substitute instead of x by 0 or instead of y by 0, the same result I will have, which equal to 0. As you can see, the first direction give me 1, which is when y equal to x. The second and third directions give me 0 when x are moving around, across the x-axis or the y-axis. I can use plenty of curves or relations or directional directions, like for example y equal to m of x, and in this case I will replace y by m of x and simplify this case, and I will be having the limit is equal to 2m divided by 1 plus m squared, and will depend on the value of m. From all of this, this is the truth in front of us. The truth defined in front of us, if you are studying the case of a function in several variables, there are plenty of methods that, there are infinite number of uh, uh, directions that you can use to find the value. And for you to know, it is just enough to have two directions giving you different limits to be sure that the limit doesn't exist. So for this problem, there is two limits not equal to each other. At least we have more than that. So the limit doesn't exist, or there is no limit near the zero, as you can see. So there is, since there is two limits not equal, then this limit doesn't exist near the origin, as you can see. Now, studying limits along nonlinear paths. In the case of studying limits along nonlinear paths, I will do the same. It's going to be exactly the same. Just I will use function with nonlinear relation, like this one. For this problem, 2x squared y divided by x to the power of 4 plus y squared, I will use y equal to x squared, for example. So if I tried to do this, okay, for the relation of y equal x squared, the result will be that I'm replacing y by x to the power of 2. That leaves you with 2x power 4 over x power 4, which is 1. If you do the same for this function with the direction of the x-axis or the y-axis, the limits will be zeros. And so once more, the limit for this function doesn't exist. Another problem here in front of you, 2x cubed y divided by x squared plus y squared. That's the shape of the function. I'm introducing the case if for x-axis or y-axis also they will exist and they will be zeros. But if I introduced y equal to x cubed, replacing y by x cubed, I will have 2x cubed times x cubed, and simplifying our life is equal to 1, and once more the limit doesn't exist. So the problem with the limits along paths or directional limits is it is really very difficult to find the value of a limit of the function, because you will never be able to grab all the directions where x is approaching certain value in multivariable functions. Also, one of the very famous methods is the iterated method, or the iterated limits. We speak of iterated limits when we compute in a sequence the limits for each of the variables that are arguments of the function. So in R2, if we want to find the limit of f of xy as xy tends to 0 and 0, the iterated limit states that I can take the limit first for y equal to 0, then I will do limit x tends to 0, vice versa, and study the case. In order to make things more clearer, let's see this problem. I have f of xy, which is x minus y over x plus y. I want to discuss the limit around the origin of this problem. So I will consider a sequence of the iteration of approaching this value by considering, if we take the limit of f when x tends to 0 first, then I will apply y2 tends to 0, which means I will squeeze around x and see what's happening around y. So once more, limit the function when y equal to 0 will leave you with 1 over 1, which is equal to 1. If I try to do the same, it's a confirmation. Here we go. That's the limit of x and y around 0 and 0. So I'm reducing y. So I'm taking the limit first for y equal to 0. So I'm putting y equal to 0s. It will give you with 1. Similar debate if I do the opposite of this relation, getting x first equal to 0, then discussing the value of y. And in such a case, you will find with a similar manner that the limits doesn't exist, because the limits when x tends to 0, then y equal to 0 is different than y equal to 0, then x equal to 0. And so the limit doesn't exist at the origin. And if I try to use the directed method by choosing the line y equal to x and make a substitution, you will end up having x minus x, which is 0, divided by 2x. The result is going to be 0. So once more, these two limits are not equal to each other, then the limit doesn't exist. Also, the discussion at y equal to x confirms the same meaning. So from all the previous, we can conclude that if two iterated limits exist and do not equal, then the limit doesn't exist. But what if they are equal? It is not a confirmation. This is a very important declaration. And if the limits exist, it is not a confirmation on the limit existence in this case. We will need to check using first principle as we did previously. So for example, for this problem, which is x squared y squared divided by x squared y squared minus x minus y, if I used the directed method y equal to x and make the substitution and make a simplification, it's going to equal to 1. Let's do it once more for y equal to negative of x. Making the substitution and also once more it's gonna equal to 0. The two directed curves y equal to x and y equal to negative x, they are not equal to each other, so the limit doesn't exist. For this function doesn't exist. Let's see by the iterated method for this problem also, x squared y squared. If I used x first, then y, or y first, then x tends to 0. Also, that's the funny thing that I told you about. Also, although in the iterated method, putting x first equal to 0, y first equal to 0, and then discussing the case of x is going to be 0, doing the vice versa is going to equal to 0, which means a very important statement, as you can see. The iterated method give you two equal values of the limit. So although the limit by the iterated method exists, but it doesn't guarantee the existence of the limit as you saw from the iterated. Fun facts about this part. If an iterated limit doesn't exist, the limit may still exist. And we already saw something like this. This is because iterated limits may correspond to bosses, which according to the domain may not be followed in some cases. Summary of all what we did. If all existent iterated limits and all limits along bosses tried are L, then the limit may be L or may not. How to be sure? Use the first principle. And this is why, because it is impossible to check all bosses. If an iterated limit doesn't exist, so it is done. The limit doesn't exist. Because iterated limits maybe correspond to bosses which, according to the domain, may not follow. A similar debate if at least two iterated limits exist and yield different limits, then the limit doesn't exist. Finally, a function where the limit exists. I won't show you this example. It's really very simple example, and you will see if I have 2x squared y divided by x squared y squared, and I'm trying to take any direction. Let's take the direction of on the x-axis, along the x-axis, which means y equal to 0, which will lead to the limit of this function equal to 0. Once we do working on the x-axis means y equal to 0. The denominator is going to be 0. The denominator is going to be x squared. The result will be 0. If I did it once more, directional limit, but using the y-axis, in this case, x will be 0. So making the substitution, it's going to be 2 times 0 y, 0 over y squared, which also equal to 0. Once more, if I use y equal to m of x and then make the substitution, So it's gonna be 2x squared m of x plus 1 plus m squared x tends to 0, it will give you 0. So all the directed methods or the directed curves give me a 0. Also using the directional limit along yx squared leads to the same fact. Even if I saw the iterated method, it will give you the same fact. So according to all of this, now we can confirm that the limit exists and it is 0. No, we still have a strong suspicion to confirm. We will have to check it first by the first principle in order to be sure about all of this. Change of variables, remark that most of the problem we solved were discussing the function approaching the origin or around the origin. But what if it is approaching something else, like xy tends to 1 and 2, for example? In this case, we will make a change of variable like the problem that we saw previously, just replacing x minus 1 by ay minus 2 by b, and do the replacement. You will get back again with the function limit a and b equal to 0 and 0, which is x squared y divided by x squared y squared, the previous problem that we already solved together. This is one of the statements state the right answer, false or wrong. If every directional limit of a function at a given point yields the same result, then there must be a limit of the function at that point. Is it true or false? Of course it's false. There is no confirmation. You will have to use the first principle to check all of this. Please, I want you to see this problem. This is a very nice problem. I solve it for you. For this problem, I will do x tends to 0 from positive and x tends to 0 from negative. I've already solved it and sent you the PDF, so there will be no problem. I know I'm sorry for being so long in this lecture, but just go through it. It's straightforward. Also, I left you with some problems I want you to solve in various cases. Please try to solve them. I solved some of them with you, but I need you to try them on your own, taking the same steps, and that's really very important to go through. Thank you very much for attending this lecture today. And I'm so sorry that it has plenty of ideas and plenty of problems, but please, I beg you, I need you to resolve these problems once more using your pen and your paper, and inshallah, all will be fine. Thank you very much for attending and for listening to this lecture. It was my pleasure to be with you. I hope you get the best of it. Best to you, and wish you always the best in your academic endeavors. Thank you. Thank you very much.